The skills that we're looking for are going to be to relate what I call the angular world or realm and the linear world or realm. And we talked about this a little bit because when we think about linear, we tend to think about things moving in a straight line. So when we think about linear, we're like, well, something is moving like this. When things are moving in along a circular path, though, we can still think about this as being a straight line. We just have to like mentally or mathematically straighten it out. So when we think about the linear realm, we're thinking about both of these things. If I want to know how far something moves in meters along this path, that is effectively equivalent to how long it would move in meters along this path. And when we think about rotation, we're not using units of length. We're using units of angles or rotation. So if I tell you that a record player spins 3 times, that does not tell you how far the record spun in meters. It tells you that it went around 3 times. If you want to know how far it went, you have to know more information than just how many times it spun around. We can use angles, we can use rotations, and those are what I'm going to call the angular realm, or we can use meters and feet and inches and yards and miles, and that's what we call the linear realm. So we're going to learn to relate that stuff. And then we've got a bunch of new variables to work with. You saw most of those on Tuesday during class, but there's some more, and they all have the unfortunate commonality of being Greek letters. Some of you think in symbols anyway. I had a student years ago who would just, instead of variables, he would just use like smiley faces and little balloons and stuff. That was a very symbolic thinker. Most of us, and I include myself in here, are pretty comfortable with variables that are regular letters, like English alphabet letters. But as soon as you throw Greek letters in there, it gets weird for some of us. It definitely does for me. I'm more comfortable with some than I am with others. The ones that we're using today, I'm super comfortable with. When you show me a partial differential, my brain breaks a little bit. How many of you are doing partial diff? Anybody? Yeah. So that, you know what it looks like? It's that weird, like, I don't even know what letter it is, but I look at that, and because it means nothing to me, my brain breaks a little. That's going to happen with some of you when we look at these variables. And then the problem solving. And I'm going to come back to this, because ultimately, as I said before, the goal here is not for you to memorize a bunch of definitions or be able to use equations in a formulaic way. Like, I do not want you to just be able to solve book-style problems. What you need to be able to do is solve real problems that involve real things in the real world, which you will, but we're going to start with this. All right, so I mentioned on Tuesday that when it comes to measuring rotation, we typically are going to use radians. So just to clarify a little bit, when we think about objects that are rotating and moving on a circular path, like if this right here were a rotating platform, like a record player, and we were viewing it from above, and it was spinning, let's say like this, counterclockwise, which is often how we're going to think about things spinning. If we were to put a penny right here and another penny right here, and then rotate it counterclockwise once, they would not move the same distance. The inner penny would move a few centimeters. The outer penny, to me, that looks like more than a meter. That's true of all rotational systems. And if you are looking at a rotating platform with things on it, that's really no different from looking at a single object rotating in space that can be moved relative to the center of rotation. So this is spinning a lot less far in one rotation than this is. But they have in common that they're rotating the same amount. When we talk about a rotation, everything on this rotating platform rotates once. If I have 2 wheels of different sizes, gears of different sizes, if they spin around once, that's one rotation. Every point on those objects is one rotation, and the object itself is one rotation. We can talk about half rotations or quarter rotations. We can also talk about degrees, right? If something rotates 90 degrees counterclockwise, zoop, that's pretty easy. And if something rotates 180 degrees, that's halfway around. Like, we can get all this stuff pretty easily. Most of us think in rotations and degrees pretty fluently. The problem is that when we're trying to move back and forth between how far something moves in inches or feet or meters and how much something rotates, the most convenient unit to use is radians. So we're going to be using radians, and there's a couple of things to think about when it comes to radians. First of all, they're just another unit of rotational distance. If something rotates 90 degrees, yoink. If something rotates 1/4 of a turn, yoink, it's the same amount. If something rotates pi over 2 radians, same amount. So it's just another unit of rotations. It's the equivalent of using inches versus yards or meters versus feet. You can use any unit you want. It's all the same when it comes to communicating how far something has rotated. But sometimes we use different units for other purposes, for convenience. Maybe it's because we're used to using a particular unit. So if I tell you how quickly I'm driving in my car, I'm going to use miles per hour, not feet per second. Those are both units of speed. But if I tell you I'm going 11 feet per second, you don't have a visual for how fast my car is going. If I tell you I'm going 30 miles an hour, you do. Sometimes we use units because they're easy to convert. So meters is a great example of that. I mean, meters are relatively recent. Those were not around for most of human history. But some brilliant, like Jonathan Metric or whoever came up with meters was like, I know, instead of having absolutely ridiculous conversion factors, let's have everything related by powers of 10. And thus we have the meter and the centimeter and the kilometer and the millimeter, which are easy to convert to each other, instead of yards and inches and feet, which aren't. And so when it comes to using radians for units of angular motion, it's the conversion. The conversion is easier with radians, so that's why we're going to stick with radians. It gets a little confusing because we're not going to move away from degrees. Basically, we use degrees when we're talking about fixed angles of one thing relative to another thing, like a ramp relative to the ground, or a string relative to a vertical surface, or like that flagpole relative to the post that it's on. Those angles we're going to refer to in degrees because we have a visual. Typically what we're going to do with those degrees is use our trig formulas to break things into components, forces, momentum, or velocity. With angular motion, we're not going to be breaking angular motion into vector components. We don't need to. We are going to be able to ignore the whole vector stuff. And if we use radians as our unit of measurement, we're going to get a lot more traction when it comes to kind of switching back and forth between, okay, it made one rotation, but how far did it go in meters? We'll talk about this a little bit more in a second, but just understand that there are some relatively simple rules of thumb for dealing with radians. The first is, if you remember that one full rotation is 2 pi radians. 2 times pi, pi is about 3.14, so it's about 6.28 radians per rotation. And if there's 2 pi radians in one rotation, then there's half of that, or pi radians in half a rotation. And pi over 2 radians in a quarter, or 3 pi over 2 in 3/4. And we can also get the 45s as well, right? This is going to be pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Those are relatively easy to remember, especially if we just stick to the 90-degree angles, right? Pi over 2, pi, 3 pi over 2, 2 pi. That's our quarter rotations. And so those are often all we need. Much of the time we're going to be thinking in terms of quarter rotations of something. The other time that it's useful to have just like a visual is when you have a decimal. Thank you. Wait, hold on. He's not here. Hang on, let me just check and see if somebody else is here. Okay, everybody else is here. Thank you so much. The other time that it's useful to have a visual is when we just have a decimal number. Like if I tell you something is rotating at 12 radians per second, then like how fast is that? What does that actually look like? And for that, so those of you who are getting these, you're going to go to the little room across from Mock's room. If you don't know where that is, somebody else that I just gave those to knows. So pack up your stuff, good luck on the test, head over to the room across from Mock's room. The rest of us are going to keep talking about, I don't know who's luckier here. Some of you have to take a test, the rest of you have to listen to me. It's all punishment. This is like when they tell you that, like, of the 10 most stressful things that ever can happen to somebody, like number 3 is divorce, but number 7 is marriage.
This is like number 50,000.
Oh, sorry, I honestly did not mean to get that to you. I know who you are. I know who you are. Okay, so the rest of us, we're going to keep talking about this. So here's what I want you to think about. If there are 2 pi radians in one full rotation, that's a little bit more than 6. That's 6 1/4. What if we just think of it as 6? What if we just said there's about 6 radians in one full rotation? That means, since there's 360 degrees in a circle, that means each radian is about 60 degrees. Not exactly, but about. So 1 radian is roughly here. 2 radians is roughly here. 3 radians is roughly here. And 4 and 5 and 6. And that's not exact, but it's close enough for like just visuals. So if I tell you that something is rotating at 12 radians per second, and you think, oh, well there's 6 radians in a full rotation, that's about 2 rotations a second. You went from being like, what in the heck is a radian to, okay, 1, 2, 3, it's rotating about this fast. So that is helpful, a visual of a radian, about this much. It's about 60 degrees, a little bit less than that, okay? When it comes to direction, I mentioned that we're not going to have to break things into vector components, and that's because when things are rotating, we're effectively going to be thinking about their motion as being one-dimensional. It's often going to be the case that we are kind of moving back and forth between thinking about linear quantities, like meters, and angular quantities, like radians or rotations. But either way, we're going to use the same frame of reference. The frame of reference that we're going to use is going to spin with the object that we're looking at. So if we have like a point on the outside edge of this wheel, like this red dot right here, at the moment that it's right here, we're going to use this frame of reference. We're going to have our x-axis be this way and our y-axis be this way. As this object rotates, the frame of reference will rotate with it. So it's now going to be here. The origin won't rotate with it, but we're going to imagine that like our x-axis is curved, right? And 0 is going to be here, and as it rotates, we'll just keep adding to our motion. So it's like taking a circle like this, turning it into a big long line, and if it rolls around again, then we just like add another line to it, where this line will be equal in length to the circumference of the circle. The signs of our motion are going to typically we're going to follow conventions for the most part, but we get to decide. We don't have to use these directions, but most people will. If we look at counterclockwise motion, that's gonna be our positive direction. So something that rotates a quarter turn will rotate counterclockwise a quarter turn. Something that has a linear distance, a curved path of 6 meters is gonna move 6 meters from its starting position in the counterclockwise direction along a curved path. And we get to decide, so there may be times when we choose to have clockwise be positive. Most of the time we're gonna have clockwise be negative though, which means if we think about our rotating frame of reference, to the right is gonna be negative. Things that are moving clockwise are essentially moving right on this rotating frame of reference. That's gonna be our negative direction. We also have a perpendicular direction here. In general, we're not gonna consider motion along that direction. Our objects are gonna be moving one-dimensionally along this curved path, either one way or the other way. But in order to have something moving in a curved path, there needs to be an inwardly directed force. So we are gonna consider our negative direction toward the center of rotation. So we're gonna have a negative direction counterclockwise / to the left, and a negative direction toward the center of our circular motion. And that again is by convention. It's not gonna be unusual for you or me or books or other people to just drop the signs entirely. Because typically, when we look at an object's motion, circular motion, it's not gonna be moving in the y-axis at all, and which means it's not gonna be moving closer to or farther away from the center of rotation, which means we don't really care that this is positive and this is negative. It just doesn't matter. We're gonna be looking at magnitudes of things like forces and acceleration. And when we think about its circular motion, much of the time we're gonna deal with things that will only rotate in one direction as we're looking at them. And so and that's not always the case. Like with the ladybug activity that we did on Tuesday, that platform could rotate both ways. You could have positive rotation or negative rotation. But with a record player, a real live record player where you put a record, it only rotates one way. It rotates as you're looking down on the top in the clockwise direction. So with a record player, even though it's rotating in what we would typically call, oops, this is positive, sorry, what we would typically call the negative direction, if you're dealing with record player rotation, you might as well just leave it all positive, because it's never gonna go backwards. Things that can go in either direction rotationally, we'll need to know which is negative, which is positive. And typically it'll be counterclockwise is positive. Things that are fixed and only rotate in one direction, we probably will just call that the positive direction. When it comes to thinking about radians, in addition to just kind of having that picture of one radian being about 1/6 of a circle, we also need to be able to relate it to rotations and to degrees. So we actually have some conversion factors, which are that one rotation, one full revolution of something is 360 degrees. And we'll see in a second that that means that there's going to be 57.3 degrees, about 60 per radian, and about 0.16 revolutions, about 1/6 of a revolution in each radian. And here's why. It's because a radian is defined by using the ratio of the arc length to the radius of a circular path. So if we think about the radius of a circular path as the distance from the center of rotation to the location of the object moving along that path, it's not necessarily a circle, right? Like if I have this object right here and I move it like this, it's not moving in a circle. There is no circle here, but it's following a circular path. And if it continued, it would make a full circle. If we looked at the path of that object, it would make a full circle. This isn't a circle. This is a string attached to a gewgaw. But we can think about its motion as being a circle. And if we think about the length of the curved path that it travels with respect to the radius of the curved path that it travels. We can use the ratio of those two things to define a unit. And that's what we've done. We've defined 1 radian as being the angle at which S, which is the arc length, is equal to R, which is the length of the circular path. And arc length means how long this curved piece of circle is if we were to straighten it out. So if you imagine taking, I don't know if I have a flexible ruler. Imagine taking a flexible ruler here and measuring the length of this curve. That's about 16 centimeters. The arc length here is 16 centimeters, and if I straighten it out, I can see that my radius is about 16 centimeters as well. So this angle is 1 radian. That's by definition. That means that if we think about the full circle, that we've got to have 2 pi radians in the full circle. 1 radian is when the arc length is 1 radius. The relationship between radius and circumference is there's 2 pi r radiuses in one circumference, which means the angle of 1 full rotation is going to be 2 pi r divided by r, which makes it 2 pi. So there's 2 pi radians at 360 degrees. So we could come up with a conversion factor that there's about 57.3 degrees per radian. And we can think about rotations as well. There's 1 rotation in 360 degrees, which is equal to 2 pi radians. So we can convert between rotations, degrees, and radians. We don't want to do that. Like, as much as possible, we'll want to just work with radians, but our world doesn't work with radians all the time. It's very common for people to think instead about rotations. So what we're going to do next, I'm going to make a quick detour here and show you something, and it's going to be embarrassing how poorly I draw this, but it's worth seeing. So if we think about how objects are moving along their curved path in terms of meters, we can also think about how fast they're going in terms of meters per second. We could also think about their acceleration in terms of meters per second squared. But if it's moving along a curved path, we have all these angular quantities we can think about as well. We can think about the angle it moves through. That would be its angular displacement. We can think about how quickly it's rotating. That would be its angular velocity. And we can think about how quickly its rotation is speeding up or slowing down. That would be its angular acceleration. And it turns out that in real world situations, we need to convert between these things all the time. So I'm going to give you an example, and this is where my horrific drawing skills are going to come in. So, hang on. I can't do this the way that I wanted to. I've got to make a change here. Sorry. Okay, so let's say that we're looking at a bicycle. So this is my horrible drawing of a bicycle. I've been practicing this for years, and it's embarrassing, but it kind of gets the point across. This is roughly what a bicycle looks like. It's got a front wheel, it's got a back wheel. That was better than first period. They were roughly the same size there. And then there's handlebars and a seat, and here's what we're interested in when it comes to bicycles, okay? One is, we might be interested in things like, well, how fast is the bike going? And how far does it go? Those tend to be linear quantities, right? Like a bicycle's gonna go 20 miles an hour, or 15 miles an hour. How far does it go? Like 6 miles. We also might be interested in something like cadence. How many times is your foot moving in a circle as you ride a bicycle? Those of you who ride bikes know that's actually a thing. People talk about like how fast your legs are spinning around. So when you push on the pedal, it makes this front gear circle travel around in a circle. And you can, if you push the pedal around once, then this gear will rotate around once. They're coupled together, they're bolted together. So one revolution of a pedal means one revolution of this set of toothed gears. That's attached to a chain that goes to another set of toothed gears that's attached to the rear wheel. But here's where it gets weird. These are two different sizes. If I rotate one full rotation here, my front tooth gear moves around once, but the back one doesn't move around once, because they're different sizes. And the back one moving will cause the back wheel to move. So as this back gears, as the rear gears spin, the tire will move as well, and that's what causes the bike to go. So if you want to know something like how does your pedaling cadence need to change in order for you to accelerate from 4 to 7 miles per hour on your bicycle, you have to think about how fast your bicycle is going, relate that to the rotation of the back wheel, relate that to the rotation of the back gear, relate that to the rotation of the front gear, and use that to figure out how your pedaling will change. And this is the kind of stuff that, like, it's hard because I know not everybody here is interested in the engineering stuff. You just might not care, and that's fine. But understand that the reason that we make a big deal out of this, what I'm about to show you, is because these kinds of problems are real engineering problems. If you're working with any kind of mechanical system, it will almost certainly have parts that rotate. If nothing else, almost every mechanical system we have has some sort of a little motor in it now. Everything is motorized. If you get in your car this afternoon and you flip the lever to roll down the window, a motor turns a little like rubber gripper thing, and that causes the window to go up and down. And you better believe the car manufacturers know exactly how big all that stuff needs to be for your window to go up and down at a reasonable rate of speed. Wouldn't it be great? Yeah, exactly, right? Like if you push the button down, your window's like ding, 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 you know, like McDonald's is closed by the time you can talk to the drive-thru. Or if you like, you know, like you're driving down the road and you open your window and it's a little bit cold, and so you start to roll it up and it's like, that would drive people crazy. We know, like we have to know how quickly the window is gonna go up and down. It's the same basic principle, right? The motor is spinning, that causes the little rubber thing to spin, that causes the window to move up and down. Even a yo-yo works on the same principle. All of these things have to be done. So when we start thinking about our rotational motion, it unfortunately is going to be necessary for us to frequently, translate between how far, how fast, how quickly something is accelerating in terms of meters, and meters per second and meters per second squared, and the equivalent values in terms of spinning speed. So here's the information that you need to know. When we look at angular displacement, that is how far something rotates, our preferential unit there is going to be radians. And it has a definition. The amount of rotation in radians of an object is always going to be equal to S, which is the arc length. We can think of this as being kind of like our linear displacement, right? But it's linear along that curved path. So straighten that path out and it's a line. But if you watch it, it's not actually moving in a straight line. Divided by the distance to the center of rotation. That is the definition of angular displacement. Divide those two numbers by each other. How far did it go in meters? How far away is it from the center of rotation in meters? There's your angle in radians. Just like when we were talking about linear kinematics, we can also think about how quickly something is moving. And that, as you could probably imagine, is going to be called angular velocity. That will get measured in radians, preferentially per second. Not always, we can do RPMs, rotations or revolutions per minute. We could do like degrees per hour, but our equations and conversions are all going to be built around the idea that we're measuring our angular distances in radians and our times in seconds, okay? And the symbol that we're going to use for that is one that's new. It looks like a W, but it's not. It's a Greek letter omega. It's a lowercase omega. And for those of you who don't remember this or never knew, our symbol for angles is typically going to be theta, the Greek letter theta, again, lowercase. So angular velocity is similar to linear velocity in that it's displacement divided by time. Only our displacement is going to be our angular displacement divided by the amount of time that goes by. But since our angular displacement is related to our linear displacement, our angular velocity is also going to be related to our linear velocity. So we can think about an object's rotational motion as being in radians per second or being in meters per second. Those are going to be the preferred units that we use. And angular acceleration is the same basic idea. This looks like an A, but it's not. This is the Greek letter alpha, a lowercase alpha. And alpha, just like acceleration, is equal to change in velocity divided by change in time. Only since alpha is an angular quantity, our change in velocity is also an angular quantity. Change in angular velocity divided by change in time. And since angular velocity is related to linear velocity, angular acceleration will be related to linear acceleration. If we know the linear acceleration of an object, we can divide that by the distance to the center of rotation. That will tell us the angular acceleration. This little t here, A with a little t, is because when we think about rotating systems, there's actually a few different types of acceleration. The only one we're going to look at today is tangential acceleration. That is the acceleration of the object along the curved path that it's following. There's other kinds of accelerations we can look at, but this is the one that we're interested in today. How quickly is its speed changing as it moves around in a circle? An object moving at a constant speed has an angular acceleration of 0. An object that's speeding up has an angular acceleration that's non-zero. In this case, I'm moving in the negative direction and speeding up in the negative direction, so that would be negative acceleration. Negative angular acceleration and negative tangential acceleration. The angular acceleration would be measured in radians per second. The tangential acceleration would be how fast it's moving in meters per second, or how fast it's accelerating in meters per second squared. These linear values, because the displacement, velocity, and acceleration all change depending on where something is. The angular values don't. If I were to look at every point along this string as the giga rotates, every point along this string in the giga itself are all rotating at the same rate. If I spin faster, the acceleration is the same for all of them if I'm looking at angular acceleration. But if I look at the linear quantities, it's not the same. The parts of the string that are closer to my hand are not moving as far in each rotation as the giga is. The giga is moving a lot. This is close to a meter in linear distance as it makes one rotation. But the string right next to my fingers is only moving a few centimeters, which means the speeds and the accelerations vary as well. The farther away you get from the center of rotation, the farther something goes, the faster it goes, and the larger its acceleration must be. So algebraically, we can just work backwards here. If we want to know an object's linear displacement, we can simply multiply the angular displacement how far away it is from the center of the circle, as long as our angle is measured in radians. If it's not measured in radians, then we have to do some pi and some 360ing, which isn't a big deal. If you tell me something moved 10 degrees at a radius of 2.5 meters, I can tell you how far it went. I just have to take 10 and divide it by 360 and then find the circumference of a circle and then multiply that fraction by the circumference. Or, instead of using 10 degrees, I can say it moved about 1/6 of a radian, in which case multiply 1/6 by whatever it is that the distance from the center of rotation was, and I'll get my distance. Okay? We will typically refer to that as S, the arc length. In our linear world, that's what we were calling delta x, change in position. Okay? But it's a curved path, so we don't call it delta x as much. We can, but usually we use S for arc length. With velocity, same deal. If I want to know how fast something is moving on our rotating frame of reference, I can multiply its angular velocity in radians per second by the distance to the center of rotation, and I'll get its linear equivalent velocity. And same with tangential acceleration. It's equal to, this is an alpha, not an A. Alpha will have units of radians per second squared. So what's on the left-hand side, what's on the right-hand side is the same thing. I've algebraically manipulated it. Delta theta is S over R. S is theta times R. Omega is V over R. V is omega times R. Alpha is tangential acceleration over R. Tangential acceleration is alpha times R. It's the same thing. You don't have to memorize or know 6 equations here. It's just, you gotta think about what you have and what you want. So if we go back to the bicycle example, if I know the radius of my back wheel and I know how many times it rotates, then I know its angular displacement. And I can use that to find the arc length. I can use that to find how far it goes. So these are new, but they're not earth-shattering. They're certainly not difficult to use mathematically. If I were to tell you right now, an object has a linear equivalent velocity of 2 meters per second as it moves along a circular path. If the object is 1.5 meters from the center of rotation, what's its angular velocity? Every single one of you could put those two numbers into a calculator and be good. Where it gets weird is that you're not going to be given those numbers like that. In real life, it's more like when you pedal once around, how far does your bike go? What do you put into what? Like how do you figure that out? Those are real world measurements and calculations that you need to make that involve these conversions. Okay, the last piece is kinematics, angular kinematics, and the good news is that all of the same rules for angular kinematics were true for linear kinematics. So that it's the same, essentially the same system, which is we have to have constant acceleration. And in our angular world, our constant acceleration is angular acceleration, or alpha. But since alpha and tangential acceleration are related, tangential acceleration will be constant as well in this case. When we have constant acceleration in a linear system, that comes because we have a constant net force. In angular systems, force is important, but it's not the only thing. We have to think about something more called torque. This symbol right here is a tau, and it stands for torque. And you don't need to know anything about torque right now except to know that A, it's different from force, and B, overall torque has to be constant for angular acceleration to be constant. There's a Newton's second law for rotating systems. Sum of forces equal mass times acceleration. The sum of torques will equal rotational mass times angular acceleration. Okay? And that means that we're gonna have the same three equations that we used before, only instead of x's, we have thetas. Instead of v's, we have omegas, and instead of a, we have alpha. The equations are the same. You can even use the solver. It all works just the same way. Our final angular displacement will equal our initial angular displacement plus initial angular velocity times time plus 1/2 the angular acceleration times time squared. Our final angular velocity will equal our initial angular velocity plus angular acceleration times time. And our final angular velocity squared will be equal to our initial angular velocity squared plus 2 times the acceleration times the angular displacement, theta minus theta naught. And all of those things are the same setup as our kinematic equations before. You can use the same solver. When you use the solver, the trick is you either use it all with linear quantities, meters per second squared, or all with angular quantities, radians per second squared. You can't mix and match. I can't put a linear acceleration in here and expect to get an angular velocity out of it. Okay? And we talked about motion graphs, and the motion graphs had, I think most of you, I hope, remember that when we looked at position versus time graphs, they were generally these quadratic curves. Velocity versus time graphs were linear, and acceleration versus time graphs showed constants. And depending on the initial signs and which ones of these things were zero, we would see some sort of pattern like this. These same patterns hold with angular motion. If we have a constant positive angular acceleration, we have a starting angular velocity that's a positive number, and we have an initial angular position of 0, these three graphs will represent the angular displacement, the angular velocity, and the angular acceleration over time. All right, so here's where it gets crazy. When we start solving problems with this stuff, even though you've used these equations with slightly different variables a billion times, and even though the other equations I showed you were pretty simple, theta equals s over r, omega equals v over r, alpha equals tangential acceleration over r, as soon as we start applying it, it gets tricky, gets really tricky. So here's the first kind of scenario here. So here's what I want you to think about. Back when I was your age, we didn't have CDs actually when I was your age. Okay. Back when I was 10 years older than you, everybody had CDs. That was like the great way to listen to music. And the way that a CD works is it spins around in a circle, and there's a laser that reads it. The laser shines on the disc and basically measures the reflection off of it. You can either have like a big reflection or a small reflection, let's say. And that tells you whether it's a 1 or a 0 at that location, and all those 1s and 0s added together make music. And as the disc is read, the laser starts about here, and the disc spins around, and it's in a groove, a spiral groove. And so as the disc is read, the laser moves out toward the outer edge of the disc. The crazy thing about it, though, is that that laser is calibrated so that it has to read data at exactly 1.2 meters per second in a linear equivalent velocity. So that means as that disc rotates, directly underneath the laser, the velocity has to be 1.2 meters per second.